Hi, this is Stewart. In today's video, we're going to talk about some applications of integration. We'll start with the area between curves and move on to average value. First, area between curves. We're familiar with the notion of the area under a curve. For instance, the integral from a to b of f of x dx describes the area between the curve y equals f of x and the x-axis between x equals a and x equals b. Similarly, the integral from a to b of g of y dy describes the area between the curve x equals g of y and the y-axis between y equals a and y equals b. Okay? But how can we talk about the area between curves? So if we have the curve y equals f of x and the curve y equals g of x, how do we get the area enclosed between those two curves? In particular, what is the area enclosed between the curves y equals f of x and y equals g of x between x values a and b, where f of x is greater than or equal to g of x on that interval? And we get the formula: the area is equal to the integral from a to b of f of x minus g of x dx. And the cartoon that can help us understand this formula is given below. If we're looking for this area between the two curves, so this area, we can start with the larger green area and subtract out this smaller blue area. And what we get is the original. Okay, and that's what we do when we take, this is the integral of f dx, and this is the integral of g dx. So by subtracting this from that, we get what we're looking for. Okay, let's do an example of computing the area between curves. Compute the area between y equals cosine of x and y equals sine of x from 0 to pi over 4. So what I'm always going to encourage you to do when you're approaching these problems is to draw a picture. So let's start with drawing a picture of this interval. So we have 0 here. Let's put pi over 2 here. And pi over 4 right in the middle. Sine x, we know that it's 0 at 0 and it's 1 at pi over 2. Okay, so it should look something like that. At pi over 4, you might remember the 1 square root of 2 triangle. Sine is equal to 1 over the square root of 2. Okay. As for cosine, it goes exactly the opposite. So the area that we're interested in computing is this one, this shaded region. Okay. So because cosine of x is greater than or equal to sine of x on this region, on this interval, in particular the interval 0 to pi over 4, so we use the formula assuming cosine as our f and sine as our g. So the area is equal to the integral of cosine of x minus sine of x dx, where this integral goes from 0 to pi over 4. Okay, so these are antiderivatives which we should be familiar with by now. This will be sine x minus negative cosine x gives us plus cosine x, evaluated from 0 to pi over 4. And that gives us 1 over the square root of 2 plus 1 over the square root of 2 minus 0 plus 1. Because at 0, sine is 0 and cosine is 1. So what we get is twice the square root of 2, which is just the square root of 2, minus 1. It's approximately 0.4. Okay. So that's the area that we highlighted before. We computed it just by a straightforward application of the formula. Okay, what does the formula look like if x is a function of y? Okay, so similarly, the area enclosed between the curves x equals f of y and x equals g of y between y values a and b, where f of y is the larger one on that interval, then the formula is given by f of y, the integral from a to b of f of y minus g of y dy. And we have the same cartoon here, where the area between the curves is given by the area to the left of the larger curve minus the area to the left of the smaller curve. Okay? Let's do an example applying this formula. Compute the area between x equals y cubed and x equals y squared from 1 to 2. So we should specify this is y equals 1 to 2. Then what we're looking at is, well, we know that when y equals 1, y squared, well, let's start with y cubed. So at 0, it's 0, at 1, it's 1, and at 2, it's going to be 2, 3, 4, 5, 6, 7, 8, all the way out here. Okay. As for x equals y squared, so this is given by at x equals 0, we have 0. At x equals 1, we have 1. And at x equals 2, we have 4. So 1, 2, 3, 4. Okay, so should look something like this. Okay, and let me make this blue curve a bit more pronounced. So the blue curve starts out to the left of the red curve, and then moves to the right of the red curve. Okay, so if we're interested in the area between x equals y cubed and x equals y squared, then we are going to look at this region. Oops. Sorry, it should be from y equals 1 to y equals 2, so we draw these horizontal lines, and then we're looking at this part. Okay. So, given that shaded area, what we're looking at, we'll note that the x equals y cubed is larger in that interval. So our area is given by the integral from 1 to 2 of y cubed minus y squared dy. And application of the power rule, we get y to the 4th over 4 minus y cubed over 3, evaluated from 1 to 2, which gives us 2 to the 4th, or 16, divided by 4, minus 8 over 3, minus 1 over 4, minus 1 over 3. And putting it all together, we get 15 quarters minus 7 thirds, or 45 twelfths minus 21 twelfths, which gives us 24 over 12, or 2. Okay. So again, pretty straightforward application. You find which curve is larger in the region, in the interval that you're interested in, and just apply the formula. What if no interval is given? So for some problems, you'll be asked to compute the area enclosed by two curves without an associated interval. And in these cases, you should first draw the associated curves to understand the interval we're looking for, and then equate the two expressions to find the desired intersection points, okay? So usually the curves intersect somewhere, and you're going to compute those intersection points and use those to define the interval. Okay, so let's look at this example. Compute the area enclosed by the curves x equals y to the fourth and y equals x to the fourth. Okay. Oops. So x equals y to the fourth. The simpler one, or the more intuitive one for us probably, is y equals x to the fourth. So that looks like a parabola, but it goes up a little. It starts a little bit flatter, and then it goes up a little more sharply. So we'll have something like this. Excuse me. Okay. As for x equals y to the fourth, that's just swapping the place of y and x. So you'll get something like this. You're just reflecting it across the line x equals y. So looking at this picture, the only area that I can sensibly say is enclosed by these curves is this area right here. Okay, so now we have to decide how we're going to compute this. In this case, one is expressed as a function, x as a function of y, and the other with y as a function of x. So we should choose one that we put both as. So we're going to say, let's take y as a function of x for both, so that instead of writing, so this will stay y equals x to the fourth, but then the other one, instead of being x equals y to the fourth, we're going to make this y equals x to the 1/4. Okay, the fourth root of x. And the reason we can do this is because this part of the curve, starting at y equals 0, is not really relevant to us. So this is irrelevant, because the gray area only touches the green area only touches the top part of the curve. So for that reason, we can solve for y in terms of x in this way. Okay, so now which y value is greater in the interval that we're interested in? Well, first things first, what are these points where the curves intersect? Okay, so when is x to the fourth equal to x to the 1/4 in this region? Well, that's the same as x to the 16th equals x, or x to the 15th equals 1. And plainly oh no, don't want to treat that way. Or you could also just subtract on both sides, and you can make this x to the 16th minus x equals 0. So either x is 0 or x to the 15th is the same thing. X to the 15th is the same thing as 1, which means that in this setting, x equals 1. So x equals 0 or x equals 1. So what we want is area between y equals x to the fourth and y equals x to the quarter from x equals 0 to x equals 1. And to do that, we use our formula for precisely this setup. You take the integral from 0 to 1 of the larger minus the smaller. So in this case, x to the 1/4 is actually the larger, minus x to the 4th dx. And then we apply the power rule to solve. X to the 5/4 divided by 5/4 minus x to the 5th over 5 from 0 to 1. And this is equal to 4/5 minus 1/5 or 3/5. Okay, and this is the area that we were looking for. Okay, so what we did again to get this answer was we drew both curves, we found our intersection points, and then we plugged it into the formula that we were familiar with. Okay, so throughout the discussion so far, we've been assuming that one function is greater than the other function the entire time. But sometimes f of x starts out greater than g of x, but then they switch places. How do we compute the area in that case? The formula is area equals the integral from a to b of absolute value of f of x minus g of x dx. So computing the integral of an absolute value will seem a little strange to us because most of the functions we work with, we don't have an antiderivative for absolute values, basically, is what I'm trying to say. So a way to reformulate that so that it's a bit more sensible to us is you take f minus g whenever f is bigger than g. So you take an integral over the intervals where f is bigger than g of f minus g. And over the intervals where g is bigger than f, you take g minus f. So you always want to make sure that the thing you're integrating is positive. And that's all you really need to do. So let's see an example of this. We're asked here to compute the area between y equals e to the x minus 1 and y equals 2e to the minus x from x equals 0 to 3. The first thing we should always do is draw a picture of the situation and see what curve is where. So let's do that now. Okay, so a typical exponential curve, it hits the y-axis at y equals 1. But these are a bit different. So the curve y equals e to the x minus 1 will hit at 0, 0. And it'll kind of drag out to the point minus 1 on the left, and it'll get really big on the right. As for the curve 2e to the minus x, that will hit at, because you're multiplying by 2, so at the point x equals 0, you're going to get y equals 2. And then it gets very small on the right and gets large quickly on the left. Very similar idea, just reflected. Okay, so now we have to figure out what this intersection point is and where it is relative to 0 and 3. So we know that at 0, 2e to the minus x is larger. Okay. At 0, 2e to the minus x is greater than e to the x minus 1. How about at 3? At 3, 2e to the minus 3 is quite small. It's pretty close to 0. And so that's probably going to be less than e cubed minus 1, which is greater than 1. Okay, this is greater than 1, and this is approximately 0. So at some point they switch places. So let's say 3 is somewhere over here. Okay, so we're going to be interested in this area. But as we just saw on the previous slide, we need to know what interval has the one function greater and what interval has the other function greater. So in order to get that, we need to compute this intersection point. Okay, so the intersection point, at that point, these two functions will be equal. So we'll take e to the x minus 1 equals 2e to the minus x. That means we can multiply e to the x on both sides. We'll get e to the 2x minus e to the x equals 2. Let's move 2 to the other side of the equation. Get e to the 2x minus e to the x minus 2 equals 0. And you'll notice this has a form very similar to a quadratic equation. And indeed, it's a quadratic equation in e to the x. So we can factor it like any other quadratic equation, and we'll get e to the x minus 2 times e to the x plus 1 equals 0. Okay, so whenever you have a product of two numbers and one of them and the product is 0, that means one of the factors is 0. You know, this one is always strictly greater than 0. So this guy has to be equal to 0, which means e to the x equals 2. So that x equals ln 2. Okay? So now we're going to plug this all into our formula. So we're looking at the integral from 0 to 3 of absolute value of e to the x minus 1 minus 2e to the minus x dx, and this is equal to the interval where the first function is greater. So that's, looking back at the previous page, that's going to be from log 2 to 3, plus the integral over the interval where the other function is greater. So that's from 0 to ln 2. And we take 2e to the minus x minus e to the x minus 1 dx. Okay, and then we can compute both of these integrals without too much difficulty. This is e to the x minus x minus, so the minus sign comes down when we take the antiderivative, and we get plus 2e to the minus x. That's evaluated from log 2 to 3. And the next integral gives us minus 2e to the minus x minus e to the x plus x. And that's from 0 to log 2. And this gives us e cubed minus 3 plus 2e to the minus 3 minus e to the ln 2, which is 2, minus ln 2 plus 2e to the minus ln 2, which is a half. So that's plus 1, plus, and now we get negative 2 times a half, so that's negative 1, minus e to the x, e to the ln 2 is 2, plus x gives us plus ln 2. So I believe we have full cancellation on this term. minus negative 2e to the 0 is 1, minus e to the 0 is another 1, plus 0. And when all is said and done, what we get is, so grouping terms, so we have e cubed plus 2e to the minus 3. Okay, then we pick up minus 3, minus 2, that's minus 5, minus 6, minus 7, minus 9. Oh, and we have some more constants here, plus 2 plus 1, so that's minus 6. And then we have plus 2 ln 2. Okay, so that question required us to find out where did the order of the functions switch places, where did the larger function become smaller, and that required computing this intersection point. Once we did that, we were able to split up the integral into two intervals where one function is always greater. Okay, now a quick foray into average value. So you might be familiar from statistics with the idea of an average. The average of a collection of values is the sum of the values divided by the number of values. Okay, well in calculus, the average value of a function f of x on an interval ab is the integral of the function divided by the length of the interval, i.e. f average equals 1 over b minus a times the integral from a to b of f of x dx. Okay. Visually, what the average value is if you draw a rectangle whose base is AB, the interval here, and whose height is the average value, it has the same area as the area under the curve. So what you see shaded in blue in this image. Now let's do some examples. What is the average value of sine x on the interval 0 pi? So it's straightforward to plug this into the formula. We have f average equals 1 over b minus a times the integral from a to b of f of x dx. For us, this is 1 over pi times the integral from 0 to pi of sine x dx. This is given by 1 over pi times minus cosine x evaluated from 0 to pi, which gives us 1 over pi times minus negative 1, which is just 1, minus negative 1, which is a positive 1. So this is 2 over pi. And that's the average value of sine on this interval. What is the average value of cosine on the interval 0 to pi? So same idea again, same formula. F average equals 1 over b minus a, integral from a to b, f of x dx. So same interval, so it's 1 over pi is 0 to pi, different function, cosine x dx. We have 1 over pi sine x is the antiderivative from 0 to pi. This is 1 over pi times 0 plus 0, and that's just 0. If you wanted to draw a picture to see what's going on here, from 0 to pi, sine looks like this. So the average value sits somewhere here. But cosine looks like this. So if this is pi. So the area on top cancels with the area on the bottom. So the average value is 0. Okay. And we'll finish off with the mean value theorem. If f of x is a continuous function, and most of the functions we deal with are continuous, on the interval ab, then there is some c in that interval for which f of c equals the average value. Okay, let's do an example to illustrate this. Find a value c in the interval 0 to 16, where the square root of c is equal to the average value of f of x equals the square root of x on the interval 0, 16. Okay, so the first step to this problem is find the average. So let's find the average. Okay, and we have a formula for this. F average equals 1 over b minus a times the integral from a to b, f of x dx. And this is 1 over 16 times the integral from 0 to 16 of the square root of x dx, which is 1 over 16 times this. We can apply the power rule, so we get x to the 3 halves divided by 3 halves, or 2x to the 3 halves over 3 from 0 to 16, which will give us, 16 to the 3 halves is the same as 16 times 4, or 64. And so putting it all together, we get 8/3. Okay. Next point is find c. So we're just looking for a c such that f of c equals 8/3. So that means square root of 8/3, square root of c should be equal to 8/3, but then that's just the same as if you square both sides, getting c equals 64 over 9. Okay? And that's the precise value that gives you the average value over that entire interval. Okay, and that's an illustration of the mean value theorem. You're able to find a point where the function value is the average value over the interval. And I think we'll call it there for the lecture. Thank you so much.